Hello everyone, this is Merdad and I'm going to delve into real-time system identification, focusing on two key concepts, linear regression equations and recursive least squares. We will explore the limitations of traditional RLS methods, particularly in fast time varying systems, and introduce a novel modified RLS approach that I have called Mod-RLS. This presentation will provide an overview of different RLS-based identification methods implemented in MATLAB Simulink. We will discuss the limitations and potential challenges of these techniques. By conducting simulations, we aim to determine the optimal application scenarios for RLS algorithms. Additionally, we will compare the performance of these methods with modified RLS algorithm to highlight the advantages. Performance of these methods with modified RLS algorithm to highlight the advantages. Imagine a scatter plot of data points where each point represents a pair of values of x and y. A regression analysis helps us find the best fitting line through these points, known as the regression line. The equation of this line is the regression equation. While simple linear regression with one independent variable can be visualized, regression models with multiple independent variables cannot be easily plotted. However, the underlying principle remains the same, which is finding the best fitting relationship between variables. The best fitting relationship between variables. Here are two methodologies that leverage the structure of a linear regression equation to estimate unknown model parameters. We refer to the procedure for either of the methods. Number one is offline or batch identification. It starts gathering a dataset with input and output values. After that, selecting a suitable regression model, let's say linear or polynomial and so. Then, using methods like least squares to determine the model parameters. Finally, validating the model's performance on a validation dataset. Number two is online or real-time identification. In real-time case, the data is constantly updated and the model is recalculated to reflect the latest information. It starts with initial estimates for the model parameters and then, as new data arrives, updating the parameters estimates using algorithms like recursive least squares. In the next step, RLS updates parameter estimates as new data points become available, making it suitable for real-time applications. The last step is validation, making it suitable for real-time application. It is noteworthy that linear regression can be prone to several important issues such as multicollinearity, which happens when independent variables are highly correlated. It becomes difficult to determine their individual impact on the dependent variable. This can lead to unstable and unreliable regression coefficients. Another issue may happen with outliers and influential points. Outliers or data points that deviate significantly from the overall patterns, and influential points which have a disproportionate effect on the regression line can distort the model and its predictions. The next issue might be heteroscedasticity. This occurs when the variance of the residuals, the difference between observed and predicted values, is not constant across different values of the independent variable. Heteroscedasticity violates one of the assumptions of linear regression and can lead to biased and inefficient estimates. One more issue might be nonlinearity. If the true relationship between the variables is not linear, a linear regression model will not accurately capture the underlying pattern, leading to biased predictions. The last but not the least is overfitting and underfitting. Overfitting occurs when the model is too complex and fits the training data too closely, leading to poor performance on new unseen data. Underfitting, instead, occurs when the model is too simple and fails to capture the underlying patterns in the data, leading to poor performance on new unseen data. Underfitting, instead, occurs when the model is too simple and fails to capture the underlying patterns in the data. As an example, we employ a simple RC model of a lithium-ion battery assuming time-varying parameters. While the actual system is more complex, we simplify the model to a structure with a constant open circuit voltage and a current source. To estimate the model's parameters, we derive a regression equation based on Kirchhoff's voltage law. This equation is formulated in both the frequency and discrete time domains. The regressors and output are calculated from measured voltage and current data. The three unknown intermediate parameters alpha, beta, and gamma will be estimated using different RLS algorithms. Once these parameters are determined, the main electrical parameters R0, R1, and C1 can be calculated accordingly. To initialize the RLS algorithm, we require initial estimates for the intermediate parameters and additional parameters like the error covariance matrix. Simulink provides various RLS-based tools that can be utilized for this purpose as follows. Simulink provides various RLS-based tools that can be utilized for this purpose as follows. Here we briefly present different RLS-based tools in MATLAB where we need to set the required settings of either method properly. First, RLS with forgetting factor. This method adapts to time-varying systems by weighting recent data more heavily and forgets older data to track changes in the system. The second tool is RLS with limited memory forgetting factor. It is similar to RLS with forgetting factor but discards old data after a fixed number of iterations. This method reduces computational cost and memory usage. The next tool is RLS with Kalman filter. This technique combines RLS with Kalman filtering for improved estimation accuracy, especially in noisy environments. It handles uncertainty in both the system and measurement noise. Then RLS with gradient method. It uses a gradient descent approach to update the filter coefficients. It is simpler to implement but can be slower to converge than other methods. Finally, RLS with normalized gradient method. This method improves the convergence speed and robustness of the gradient method by normalizing the gradient step size. It adapts to changes in the input signal and noise level. And robustness of the gradient method by normalizing the gradient step size. It adapts to changes in the input signal and noise level. As mentioned earlier, I have created a new modified RLS algorithm that effectively addresses both slow and fast-changing systems, either linear or a class of physical nonlinear systems. Unlike existing RLS methods in MATLAB, our Mod-RLS is uniquely suited for estimating lump parameter models of lithium-ion batteries encompassing both electrical and thermal models. The flowchart outlines the complete real-time parameter estimation procedure with Mod-RLS as the central component. In addition, the accompanying MATLAB function provides details in a part of the Mod-RLS implementation. MATLAB function provides details in a part of the Mod-RLS implementation. We simulated the estimation of RC circuit parameters using various methods. Two distinct periods were considered: an initial phase with constant parameters for time less than 1000 seconds and a subsequent phase with significantly varying parameters. The diagrams from top to bottom showed estimates of R0, R1 and C1 respectively. The estimation results of each method are shown in a different color in the diagram. The black color represents the actual values of the electrical parameters, all of which vary with time. As can be seen, the limited memory forgetting factor method is very oscillatory. For this reason, it is initially disabled so that the rest of the results can be seen more clearly. As can be seen, most methods have provided a good estimate in the initial region of the simulation where the parameters are constant. But clearly the RLS-based methods in Simulink have not been able to estimate with good accuracy in the region where the parameters change. In the region with parameter changes, the forgetting factor method has only been able to estimate R0 with low variance, but has not performed well in estimating the others. Finally, the proposed Mod-RLS method has estimated all parameters over time with very good performance, but has not performed well in estimating the others. Finally, the proposed Mod-RLS method has estimated all parameters over time with very good performance. To conclude, for systems with constant parameters, most of RLS-based methods with correct settings should work well. And also for slow time varying systems, some of RLS-based methods may work with correct settings. And for fast time varying linear systems, RLS with forgetting factor might work well. However, the newly proposed Mod-RLS outperforms other methods, not only identifying linear systems, but also a wide range of nonlinear fast time varying systems. This makes Mod-RLS an ideal tool for identification in challenging use cases. At the end, I would like to thank you for your attention, and if you would like more details, they are available in my papers as addressed in the following.